All right, so this question here is 2021 Math Methods 1, question 9, and this is tech free. So we've got this unit circle, and this unit circle is asking us to show that the tangent for this particular line, PA, is given by that equation. So we need to dissect a couple of pieces of information from this unit circle. Now, this unit circle here, we need to, I guess, extract this triangle that we've got here. And we can recognize that there is a length of 1 because it's a unit circle. So that length there is 1. And this coordinate here, the hypotenuse, will be 2. And as a result, we can then use this to work out that missing side, which will be root 3, because 4 minus 1 is equal to square root of 4 minus 1, root 3. So at this point, we are associating this theta angle with that theta angle there, and we want to calculate the gradient of that. The other thing that we could do is we could calculate the gradient by using, excuse me, tan theta is equal to the gradient, which is equal to rise over run. And our rise in this case is root 3. Our run is 1. But we need to consider the fact that this is for these positive angles here. So this is technically going to be the reciprocal because we are calculating the wrong quadrant. So if we consider this the gradient, therefore the gradient of AP is going to be the negative reciprocal. So I should have said negative reciprocal because it's the perpendicular line to that. So if we know that that's the case, we also know that this triangle here must be pi on 6, and as a result, this must be pi on 3 because 180 degrees in a triangle. So we can then label this here as such. So this is going to be pi on 6, and this is going to be pi on 3. All right, so let's answer the question. It says show that the equation of the line passes through that particular point. So you've got our gradient, we've got a coordinate, so m is equal to negative 1 on root 3. Point is 2, 0. So we've got y equals mx plus c. So 0 is equal to negative 1 on root 3 times 2 plus c. Therefore, c is equal to 2 on root 3. Therefore, y is equal to negative x over root 3 plus 2 on root 3. And we have shown our tangent line that way. All right, just because I can anticipate this further down in the questions, I'm going to just quickly work out what coordinate P is. Now, in order to work out coordinate P, I'm going to cut this into a little triangle. Okay, and if this is pi on 3, and we know that the bottom distance is something that we don't know yet, but we know that this is 1, and we don't know that or that, we just need to, I guess, piece together the fact that sine represents the height, so that's the y values, and cos represents the width, or the x values. If we apply some sort of trigonometric ratio with this, this is the opposite and this is the adjacent, so we can say sine theta, in this case it's pi on 3, is equal to the opposite, which is what we want to find, over 1. So where is sine, what is sine pi on 3? Sine pi on 3 is root 3 on 2 is equal to x on 1. Therefore, x is equal to root 3 on 2. So we know that this coordinate here is, sorry, I should probably use y's instead of x's. Y is equal to root 3 on 2. Likewise, if we do the same thing with the cosine idea, cosine pi on 3 is equal to adjacent over hypotenuse, so a over 1. Cosine pi on 3 is a half. A half is equal to a on 1. A, or therefore x must be equal to a half. So we've got our coordinate here as such. And that'll come handy later on when we start looking at the next few questions. All right, the next question now is asking us, given this particular transformation where q can't equal 0, but it equals every other real number, find the values for q which the graph intersects with the unit circle at least once. Now, this is taken out of the study zone. However, this still is an applicable transformations question. In fact, let's do a bit of a matrix multiplication for those of you that know how to do this. X times 1 gives us x, y times 0 gives us 0, and we've got 0 times x gives us 0, and q times y gives us q. So we're almost mapping the coordinates xy to the transformation qy. Now qy talks about a dilation factor from the x-axis. So whether or not we have a high value or low value will determine how high or how low that y coordinate now becomes. Now it's saying find the values for q. So how does this actually apply in this situation? Well, in this situation here, we've got if we had a q value of 1, the graph will not change. Okay, that tangent line will remain the same. So it says intersect with the circle at least once. At this point here, it's intersecting once. So if we dilate it any further up, it will actually not intersect at all because we're going to make this graph even steeper. So this graph here doesn't change the x-intercept, but the graph will become steeper if we make the value for q greater than 1. So the absolute maximum that we can do is 1. And we can actually include 1 as well. What's the 1. What's the lowest point that we can include in this graph? Well, this graph can go all the way from here, 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 even here, if we reflect it. Now, if we reflect it, this will have a q value of -1. And we can't go any further than this because if we go further than this, it'll shoot all the way further through and not intersect at all. So for this question, we would say the lowest value is -1. Now, the only thing that we need to be careful with this one is that the tangent line is saying that it's excluding r is equal to x equal to 0. So we need to make sure we include that in our excluding 0 in this case. All right. So that's the answer to that question. Now the next question says, let the graph h intersect the unit circle twice. Find the values of q for which the coordinates of the points of intersection have only positive x values. So let's deal with this one at a time. It says here, it intersects twice. So if it intersects twice, we know the values for q. We just work that one out. If we have a value of q is equal to 1, we get that. If we reduce it, so if we knock it down further, so if we dilate it down a little bit further, we'll get the 2 points of intersection, like for example here. You can see there's a point of intersection here and here. If I dilate it even further down, I have a point of intersection here and here. And even in the negative direction, I have a point of intersection here and here. Now, this question has put in another restriction. It's saying the points of intersection only have positive values, which means that now everything underneath this line here that I've just drawn cannot be a possibility because these will both have negative values. In fact, even up here, this will be a negative x value, but a positive y value. So they don't both have positive y values. So the only times that they can have both positive values is that if they intersect in a way that it's only in a really small section up here. The question is, what is it? So let's just put in the absolute upper bound first. So the upper bound is 1. So you can't dilate more than 1 because we knew that it kind of doesn't intersect and it just will have no intersection point. So if that's the case, the other thing we need to be careful of is what is this coordinate right here? Now this coordinate here is the y-intercept of the tangent line. And we can use that information there to say that that's 0, 2 on root 3. And if we look a little bit further down here, this coordinate here is 0, 1. In fact, we can only dilate it, so I'm going to put this in maybe in orange. You can see that this graph here, if I, to the best of my ability, draw this straight, if I have a particular angle there or dilation factor, I will still have 2 intersection points. One of them will be 0 and one of them will be positive, but at least we're working with something here. So our question is, if we can only dilate down to 1 and we've got 2 over root 3, we can use scale factors to work out the actual dilation that we want. So where we want to go is 1. Where we started from was 2 over root 3. So this means that we can only dilate by a maximum of root 3 on 2 if we want to knock this graph down so that it doesn't have, it has two intercepts. So this is going to be root 3 on 2. Now we can't include root 3 on 2 because if we include root 3 on 2, it'll include that coordinate 0, 1. And 0 is not a positive number in this instance. So we need to exclude the dilation factor of root 3 on 2. All right. All right, so this next part here is saying for Q is between 0 and 1, let P dash be the point of intersection of that graph, where P is always the point of intersection that is closest to A, as shown in the diagram below. Let the function give the, let G be the function that gives the area of OAP in terms of theta. Okay, so a couple of things I'm wary about. G, theta, and this P dash here. Now, this P dash, if I increase this gradient, okay, I'm just going to see what would happen if I make P dash a different value. So if I make P dash over here, okay, what happens is that P dash no longer becomes the that point there. So this cannot be P dash because if I set that to be P dash, the intersection point that I get will actually be closer than a particular point. So there's going to be a limit to where P dash can actually be set. So I can't set P dash too high because if I set P dash too high, it almost like resets to this tangent point as being the closest point because it intersects more than once. And the other thing I need to keep in mind is P dash. I can't make P dash over here. Well, I can there, but I can't make P dash equals 0 because if I make P dash equals 0, I end up with having some sort of line instead of an arrow. So there's going to be an absolute threshold over here where P dash will only have one intersection point. And this is why I said before that when we're talking about one intersection point, it's going to be this tangent right here. And this is why this coordinate is very useful because this coordinate will pinpoint that exact point where p hat will only have one intersection point, we're at half root 3 on 2. And if we draw the tangent line going down that way, okay, we can see that we still have a triangle over here that we can find the area of, and it's almost like set at that perfect point. Now, what is going to be the area of this triangle? We've got a triangle here, looks like this and this, and we know area is equal to half times base times height. Obviously, writing this as half times base times height is not correct. We need to express in terms of theta, and we need to have a look at how we can do that. So, um, let's look at if we can work out the height of this triangle and the width of this triangle. So the width of this triangle will be 2. What's the height of this triangle? So if we cut it right there, the height of this triangle is unknown. So area is equal to a half times 2 times the height. But this particular height, if you remember the unit circle, we can define the width as cos and the height as sine theta. And so we can say the height in this case is sine theta. So sine theta. Because remember, with sine theta, that'll change the value for p, but in this case, it's in terms of something. You're not actually asked to find an exact area. So from here, we can simplify this as area is equal to, that cancels out, sine theta. Now we need to be very careful with this one, and that we need to consider what values of theta we can use. Obviously, with theta, we have to recognize that we can't go for the 0 to 2 pi. The theta can't be a whole revolution. In fact, we can't even go past pi on 2 because that will it becomes negligible in that way. And we want to make sure this tangent point always remains in this arc right here. So this tangent point will be from 0 to what's that point? What's that angle that we calculated there? Pi on 3. So pi on 3 is the absolute peak of that, and it can equal pi on 3. I'm not sure if it can equal 0 in this case. I'm going to assume it can't equal 0. So we need to define the function. So g such that g of x, no, g of theta is equal to sine, sorry, flipped up the domain, 0 to pi on 3, mapped onto all real numbers, such that g of x is equal to, I did it again, sine theta is there. So from that point, we have defined the function, and yeah, then the next question says determine the maximum possible area of the triangle OAP dash. Now, this is the area formula. So if we sketch this graph, sine theta, okay, we get this. But we're restricting it so that it's 2 pi on 3. And pi on 2 will be that peak there. So pi on 2 will be the peak, and this coordinate here is pi on 3. The question is, what is the area if that is pi on 3? So we just need to find what is g. Pi on 3 is equal to sine pi on 3, and sine pi on 3 is equal to root 3 on 2. And that is your maximum area for that question.